Hi everyone, Mr. Rodriguez here. I hope you are all staying safe and healthy. Um, Today we're going to be looking at lesson 4, proving the area of a disk, or circle really. Our objective is students will be able to prove the area formula of a circle using inscribed polygons. And we'll unpack this more as the lesson goes on. So our lesson starts with this kind of little opening exercise here. So the opening exercise says, the following image is of a regular hexagon inscribed in circle C with radius r. Now it says, find a formula for the area of the hexagon in terms of the length of a side, S, and the distance from the center to a side. So if you look, we have our circle in black, we have our hexagon in blue. We have a side of a hexagon is labeled S. Remember, all the sides of a hexagon are the same. We have our H, which is the distance from the side to the center. So we have that information, and now we need to think about how we are going to find a formula for the area of the whole hexagon. So all the space that's in the hexagon. So one thing we can kind of notice is that a hexagon is really made up of 6 triangles, right? You see we have 6 triangles there if you count them. And we also notice that all these triangles are the same. They have the same area. They're the same triangle, same size. They are congruent. So what this actually means is if we can find an area formula for just one of the triangles, all you do is if you multiply that by 6, right, you'll have the area formula for the whole hexagon. So let's do that here. So let's say we have area of a triangle, and that's equal to, remember, area of a triangle is 1/2 base times height. So we have 1/2. But here, instead of using B for base, I'm going to use S, just because that's what they've given us, right? You can see that side S is really the bottom of one of those triangles, or the base of it. So we have 1/2 S, and then times height. And again, we said that the area of the whole hexagon is just going to be 6 times the area of a triangle. So really, the area of a hexagon, if I say area of hexagon, is going to be 6, right? And then times the original 1/2 times S times H. So we have 6 times 1/2 S H. And that is fine. That is basically a formula for the area of a hexagon. So if you were given a number for height and if you were given a number for side, you can use this formula to solve for the whole area. But I actually want to rearrange it a bit just to show you something that'll be useful later. So let's say I rearrange the formula to look like this. So area of a hexagon is equal to, and let's say 6 S times, and let's say H over 2. So this, what I just wrote, is actually the same thing as the second line, right? Because all I did was, these are all just being multiplied 6 times 1/2 times S times H. It does not matter what order you put them in. So I just decided to put the S next to the 6, right? And 1/2 H times H is the same thing as H divided by 2. So it's the same thing. So now, the reason I wrote it like this is because I want to point something out about 6S that will be useful later. So 6S here. So what do we notice about 6S? So we know that S is one of the sides of the hexagon, and if you multiply that by 6, that actually gives us the perimeter of the hexagon, right? So you can really think of this as the area of hexagon equals the perimeter times height over 2. So that's just why I rewrote it like that, just to point out that that is the perimeter. And we're going to come back to this. This formula will be useful later in helping to prove the actual area of a circle, the formula for that, which was our objective. But before we do that, we want to do some more kind of pre-work to get us ready for that. There are some things that will be helpful for you to understand. So let's take a look down at this next example over here. So it says begin to approximate the area of a circle using inscribed polygons. So again, our goal here is to get a formula for the area of a circle. So we want to start thinking about what could possibly help us do that. So it asks us, how well does a square approximate the area of a disk or a circle? And it asks us to create a sketch of P4. That really just means a polygon with 4 sides, which is a square, in the following circle. And then it says shade in the area of the disk that is not included in P4. So an inscribed polygon, right, would be a polygon or a shape that's inside the circle. So an inscribed square would look something like this. Do my best to draw it here. So a little sloppy, but something like that, right? You can see how that square fits into the circle. And now I wanted us to shade in the area that's not covered by this square. So we see over here is not covered, right? Over here is not covered, over here isn't covered, and over here isn't covered. So as you can see, the square is a decent amount smaller, right, than the circle. So it's not necessarily that great of an estimate, right? Because we have a lot of space, as you can see, that is still left over. So we wouldn't really want to use the area formula for a square to estimate the area of a circle, right? Because you'd be missing a lot of space. So let's check out for part B here. It says create a sketch of P8 in the following circle. Now P8 again is a polygon with 8 sides. So a polygon with 8 sides, you would know that as an octagon. So there's kind of a little technique you can use to draw an octagon within a circle. So again, let's first start off with a square. So let's see, we have a square here. And basically what you do, this would be easier if I had a ruler. If you have a ruler, you can use one. So basically what you want to do is you see this kind of center point here. You want to kind of draw a line from the top of the circle through that center point to the bottom. So if you kind of imagine, you would have kind of a point somewhere up here, kind of a point somewhere over here. Or I should say, I'm sorry, you don't really need a full line, but you could use kind of a ruler to line up, right, with the center here. And you would have this point on top and this point on bottom that is created. And you can do the same thing horizontally. So again, if you have a ruler, if you kind of line it up with the center going horizontally, you get a point that's somewhere over here and somewhere over here. So to get an octagon now, all you do now is you see we have these kind of, we have, right, these points that are on the circle around, and you basically just connect the dots. So if you imagine up here, I could connect here to here, again, kind of sloppy, here to here, here to there. there to there, there to there, there to there, there to there, and there to there. Very hard to write with this stylus, but as you can sort of see, that is supposed to be an octagon. So, right, because you could count, it has 8 sides. And basically what I want you to notice now is, let's see how much area is left over. So we have the octagon, so you can kind of ignore the square we made in the center now. So we have the octagon as all this space kind of in the middle here. And then the amount of space that's left over is pretty small now, right? It's just these kind of little slivers around, right? It's a little hard to draw over here. Right, so it's kind of these little slivers around that are left after you draw the octagon. So what you would notice is that the octagon approximates the area of a circle much better than just a square, right? You see there's a lot less space left over. So here it asks you, which polygon has a greater area, the P4, the square, or the P8, the octagon? We would say, obviously, the octagon, right? Right, the area of the square is less than the area of the octagon. And now it asks us kind of a theoretical question. Will the area of an inscribed regular polygon with 16 sides be greater or less than the area of a polygon with 8 sides? So if you imagine if I had 16 sides instead of 8, you would imagine that there would be even less room left over. So a polygon with 16 sides would be even better than an octagon, right? It would be even closer to looking like a circle. So we would say P16, right? That would be a better approximation of a circle. And last one for E over here. So it says we notice that the area of a polygon with 4 sides was less than the area of a polygon with 8 sides, and that the area of a polygon with 8 sides was less than the area of a polygon with 16 sides. In other words, the area of some polygon with some n amount of sides, so just any kind of number, will be less than the area of a polygon with 2 times as many sides, right? Just like how we went from 8 to 16, and 16 was bigger. So if we go from some number n to 2 times n, this will be bigger here. The reason that this is true is just because as you get more sides, you're kind of covering more of the area that's within the circle. So it's getting closer and closer to that area of a circle. So I want to kind of go back now to our original kind of problem up here, and I think you'll be able to get an idea of how this area formula for a circle works. So let's take a look at our area formula up here. So we said the area of a hexagon is equal to the perimeter times height over 2. So, right, that was our formula for a hexagon. And one thing you could kind of notice is that if we were to say make this an octagon, it would be, right, there would just be more triangles. So there would be more triangles. So you would just use the same kind of formula. The only thing that would change, right, is instead of 6s, you would have 8s, right? So the idea here is that, right, you could just use the same general formula. It would be helpful for all the different kinds of polygons. And if we imagine, if we try to, say, use this for a circle now. Let's say we have So let's try to look at this for area of a circle. We have, so what is the perimeter of a circle? If you remember, that's the circumference, right? So instead of writing perimeter, we would write circumference, right? Times, again, height over 2. And now, one thing we can kind of further do here is we can kind of unpack what this means now. So we're going to kind of show how we use the reasoning from our polygons, from our hexagon area, and now we're applying it to circle, right? So we used circumference instead of perimeter. Now, if you remember what circumference is, circumference, the formula for that is just pi times diameter, right? And then, again, we just bring down the times height over 2. And now what I want you to notice here is if we do area C equals, and then pi d, diameter can actually be rewritten as 2r, right? So we have pi times 2r, right? Because the diameter is just 2 times the radius. And then times h over 2. Now, one thing you could notice is that the 2 cancels out. The 2 over here can cancel out with the 2 over here, right? Because this is like 2 divided by 2, which is just 1. So now we're left with this. Now you might notice this is a little odd. We don't usually have an h, right, in our formula for the area of a circle. But what this h really is, remember, it was the distance, like if we look back at our hexagon example here, it was the distance from kind of the edge of a shape to the center. Now, if you imagine if we did the same thing for a whole circle, right? Like if you imagine, say, let's look at the circle over here. So that would be our h if we're using a circle. But what do we usually call this? The distance from kind of a part of the circumference of the circle to the center is the radius, right? So this h over here is really just our radius. So we have AC equals pi r times r, which, again, r times r is r squared. So you can see that's our area formula for a circle. So that's how you get that. So again, we can see we started with the area formula for just some random polygon, a hexagon. We saw how we can use, right, polygons with more and more sides are better approximations of a circle, right? And then we came back to this general formula here, and right, instead of using perimeter, we used circumference, right? So we took this formula and we kind of applied it to a circle, and that's how we got our area formula that we're used to for a circle. So before you work on the problem set, I just want to do a kind of quick little example problem down here. So again, we're kind of looking at inscribed shapes still. So if we have this problem here, so notice we have a circle inside a square, and we are going to be finding the area of the shaded region. So what we do here is what we basically do, we did this in class if you remember, we take the area of the outside shape, and then we subtract the area of the shape that's inside, right? And then what's left over will be what is in the shaded region. So, for instance, here we start off with, we have a square on the outside. The area formula for a square is, right, length times width. But if you remember, for a square, the length is equal to the width. So we have 8, right? And then this would be 8 up here. And so now we have 8 times 8. And that would be equal to 64, right? So our area of the square is 64 units. But we're not done yet because we need the area of the circle. So area of a circle, as we showed, is pi r squared. So we have pi, and then our r is 4. So pi times 4 squared. We have area equals basically 16 times pi. And now to get a number, right, we can just put this in our calculator. Times. If you use 3.14 for pi, you end up getting about 50.24. And lastly, you just subtract, right, you take your area of the square and you subtract the area of the circle, right, to get your area of like the shaded region, right? Area of shaded, right? So we have 64 minus 50.24. And if we put that in, we get should get 13.76. So that's our area of the shaded region. So now that you've got that down, you've had some practice, try out the problem set for this lesson down here.